Okay, so the second talk of this session will be given by Jared, and he's going to talk about an abstract domain for heap commutativity.
All right. Let's see if I can get my mouse to work as a makeshift slide clicker. Are we good? Okay. All right. Hey everyone, I'm Jared, and like Alexandra said, I'm going to be sharing an approach for commutativity analysis in the context of the heap memory model. So for those unfamiliar, commutativity is a relational property of programs or fragments of programs, which we denote with this bow tie operator. And it holds when executing the two programs in sequence yields the same outcome regardless of the order of execution. This property is growing in popularity in a variety of domains because if you can swap the order of execution, that grants a sort of independence which is more broadly applicable than a strict requirement of disjointness of the operations of the two programs. The goal of commutativity analysis is to find a so-called commutativity condition on the initial state under which your two programs commute. And naturally, when you're synthesizing a condition like this, you want it to be meaningfully weak so that it occurs as often as possible. And aside from synthesizing a condition, you might also try to propose and verify one, which naturally is easier to actually execute on. But one context where commutativity analysis is underexplored is in the memory model of the heap, which is why we're going to target it in this work. So to start with a basic example, let's consider a typical implementation of a stack data structure on the heap. And it comes with operations for push, pop, and peek. One question we might ask is, when does pushing a value u commute with pop? Well, actually, before we can answer that, we have to decide what we consider equivalent outcomes to be. Now, there's a pretty straightforward one. In this context, let's say that we consider equivalence to be when the resultant stacks on both sides are observationally equivalent. That is, they contain the same values but may have different intermediate addresses, and that our return values of our push and pop operations are the same. So in particular, pop should return the same value in both cases. With this, we can find that the weakest commutativity condition for this program pair is that our initial stack has at least one element, and that element is the same as the one that we are pushing. So how might we show that this is a valid condition? So you might go to employ typical relational reasoning techniques, but they tend to be kind of ineffective in the context of commutativity because, in general, we're trying to compare F sequenced with G and G with F, and those usually have dissimilar shapes. So they lack meaningful alignment points, and the ways that you would typically decompose a relational problem like this don't become so useful, which means that proving this tends to amount to 4 symbolic executions for every program pair. So as your number of programs grows, the total number of executions you're having to do grows quadratically. It's not great. Now, particular to the heap, there are a couple extra frustrations to contend with. You have to consider whether your heap is well formed in the first place. So in the stack example, for instance, for these programs to commute, you need the stack to actually be well formed on the heap to begin with. And similarly, we have to contend with observationally equivalent heap structures, like having different intermediate addresses in stacks with the same values. And relatedly, this ends up coming from the non-determinism of address allocation. So what we sought to do was wrap all these things together and leverage abstraction to be able to work with this problem much more straightforwardly and simply. So with that in mind, and the abstraction we've designed, here's what our technique looks like in broad strokes. So we want to analyze the commutativity of our concrete program pair. The first thing that we do is we lift our concrete programs and our heap structures into our abstract domain, then establish a soundness relationship between our concrete and abstract programs, then analyze commutativity in the abstract space, which we'll see is way, way easier because we're going to be working with pure mathematical functions over mathematical objects for which a variety of tools and techniques already exist to do that kind of analysis very efficiently. And then finally, we will have a sound commutativity theorem which lets us immediately derive concrete commutativity conditions from our abstract analysis. And in particular, the resultant conditions will be framed. That is to say, it guarantees that if F and G commute in any particular heap context, they're also going to commute in any larger context, and we get that for free. And along the way, as I mentioned, we will easily capture observational equivalence, heap well-formedness, and as we'll see later, will also support composition of disjoint heap structures. So let's talk about what our domains look like. First, the concrete domain is simple. It's sets of heaps. Not individual heaps, but sets of heaps because, as we said, our concrete programs can be non-deterministic, so we want to account for the possibilistic outcomes of our heap program executions. Now here's where the new stuff comes in. The first ingredient for designing our abstract domain is that we pick some set of abstract values x. These could be lists, integers, booleans, sets. The choice depends on what heap structures and behaviors we're looking to lift into the abstract space. So we'll see shortly that for our stack, for instance, we may choose lists of values as a meaningful abstraction. So then in our domain, we create a lower bound of bottom, which will represent failure, and an upper bound of this little smiley face, which represents sort of an ambiguous combination of abstract elements, and we'll see the complement to the smiley face in a moment. The natural question is, how do we connect these two domains together so that we have a sound relationship? Well, our second ingredient to help this out is going to be designing a projection function pi, which maps heaps into our space of abstract values. But if you recall, we said, for the case of the stack, for example, our abstract values are lists. What if we have a heap which does not have an appropriately allocated stack? What do we do with it? Where do we map it into the abstract domain? Well, this is where we have a special abstract value come in, call it frowny face if you'd like. And this abstracts the heaps which are not well formed with respect to whatever lifting we're trying to go for. So we can add that to our domain and then top off the domain, as it were, with top. From here, now we can build our abstraction and concretization functions, which form a Galois connection. In particular, the abstraction function is real simple, takes a set of heaps, projects all of them using pi, and then yields the least upper bound of all of those results. What we get from this is sort of two key pieces to...
Can I ask a question?
Yes.
When you take the least upper bound there, because you took a flat domain, is it the case it's always going to be smiley face or close?
No, so if you have a set of heaps, so the question is, if you're taking the least upper bound, wouldn't it always just go to smiley face or top or something? No, because if you have a set of heaps, which are all, they may all map to the same abstract values. So for instance, if you have multiple concrete stacks with different intermediate pointers, but the same values within them, they'll all map to the same list of values. And so they will all end up here, for instance. As soon as you have two different ones, yes, it'll go to smiley face, or if you have something out here, it'll go to top, yeah. And we can address that more later. So what we get from this connection is sort of two key pieces to our abstract domain. The first characterizes heaps which are well formed with respect to the lifting that we've created, and we call this the purview of our abstraction. It is the heaps that it can understand and reason about meaningfully. And then in contrast, we have this piece of the domain which we consider to be the heaps that are out of purview. They have structures that our abstraction cannot understand, and therefore when we perform abstract commutativity analysis, if we get results that involve frowny face or top, we've lost precision and we won't be able to draw meaningful conclusions back down in the concrete space. And then just one more detail, we add an extra requirement to our projection function called a locality constraint, which says that if we have some heap which is in the purview of our abstraction, then any larger heap should map to the same abstract value as the original. So let's look at an example again of how this all shakes out with our stack. So like I said, we might choose for our abstract values to be lists to represent the values inside of the stack. And then the way we might build our projection function is using some separation logic style heap predicates. We would say, all right, given a heap, map it to a list S if those values in that list correspond to the values in the stack. Otherwise, if there isn't such a list, map it to frowny face. Now the stack predicate there is doing a lot of the heavy lifting. How we might implement that is with a very standard recursive definition of a well-formed stack on the heap. And just as a refresher on sort of these separation logic style predicates, we have the points to predicate, which says that the address head points to the value p in this case. And then we have the separating conjunction, which says that the heap has to satisfy both sides of the conjunction, and also both sides need to use disjoint sets of addresses. Then one more detail, we annotate this predicate stack with the plus to indicate that the heap may contain a valid stack rather than having to be exactly a stack. So we have our domains. Let's look at our programs in the concrete and abstract spaces as we sort of build up all the pieces of this diagram. So as we've said, concrete programs map heaps to sets of possible heaps. We aren't super concerned in this work with the specific concrete semantics, but so here's a sort of general implementation that you might see of push, pop, and peek for the concrete stack. You have your typical operators of address allocation, dereferencing, freeing, writing. The key thing to note here is that each of these operations has an input or an output value, but instead of having sort of this floating either external input or return, we actually provide an address to have the input get read from the heap or the output get written to the heap, so that now everything is taking place on the heap. And that makes the reasoning about these concrete programs in the abstract space a little more straightforward. Now, abstract programs, as we said, they are pure mathematical functions operating over the values in our abstract domain. So looking at an example, now we have a nice simple implementation of push in our abstract space. It takes in our list of values S and pushes the value V to it. But you might notice that push takes in two arguments, the initial stack and also this extra cell with its input argument. So in fact, this is going to be the case for all three of our operations. The abstract values for us to work with when defining these operations are not just the lists to represent the stack, but also an extra cell of sorts to encode either this input or output. So indeed, you can see with push, what it yields is that final push stack, and then it preserves that extra cell, which at this point is arbitrary because it's not outputting anything in particular. Similarly, we can define pop and peek, where they disregard that initial input, but then they use that extra cell in their output. We can see that here. And then just as one other note, when we try to pop an empty stack, you can see that we yield bottom, which indicates failure. So we have our concrete and abstract programs. Let's connect them together with a notion of soundness, which we denote with this squiggly arrow. And we say that abstract program M is sound with respect to concrete F if two things hold. First, that M over approximates F, which is a standard constraint in abstract interpretation. And then a second one, which says that M fails when F fails. And the second one is important because our notion of commutativity is going to depend on successful termination of the concrete programs. So this helps to handle that case. And the way that we would show this is using typical symbolic execution techniques. And note how now what we've done is we've said, OK, for each program, if you have n programs, for each one, show soundness once with its corresponding abstract program. And then we'll reason in the abstract space, instead of having to do those 4 symbolic executions which grow quadratically all in the concrete space. So now let's actually define commutativity, both in our concrete and abstract spaces. And then we're almost there. Then we can get to our sound commutativity result. So in the concrete space, we say that our two programs commute under a commutativity condition, a heap predicate P, and with respect to some relation on the output sets of heaps, if given a heap that satisfies that commutativity condition, executing F sequence with G on that heap gives an equivalent outcome to G sequence with F on that heap, and that both sides successfully terminates, that we actually get a non-vacuum, a meaningful outcome and no failure. You could instead define concrete commutativity using a co-termination sense, but here we're going to stick with mutual termination, or both termination. Correspondingly, in the abstract space, we say that our two programs commute under a predicate Q on our set of abstract values if given an abstract value that satisfies Q, executing n composed with m on that value equals m composed with n, so the flipped compositions, and critically, that the result is in our meaningful section of the abstract domain X. And this is because you can imagine if both results went to top, you'd say, OK, great, they were the same outcome, but we don't know anything about, top doesn't tell us anything meaningful. So we restrict what the meaningful section of commutativity is in the abstract space, which then lets us get to our sound commutativity result, our last ingredient in this diagram, which says that if we have soundness between our two pairs of programs, supposing that the abstract programs commute under a predicate Q on our values x, then we can immediately derive that our concrete programs commute under a predicate P, where a heap satisfies P if it is in the purview of our abstraction, and the abstract value it maps to satisfies Q. Two details to note here. The first is that we said that concrete commutativity was with respect to some equivalence. In particular, here the equivalence that we get is that which is imposed by the abstraction. So in particular, we get that the results on either side of the concrete execution, if they both map to the same abstract value, then they are considered equivalent, which means that the projection function that we choose sort of induces the observational equivalence that we're interested in the concrete space. The second detail is that, again, we have that our concrete condition is framed with that plus, and like I said before, that means a guarantee that if F and G commute in any particular heap context, they also commute in any larger context. So let's put this all together with our stack example. Here we have all the possible program pairs for our 3 stack operations. And like I said, we aren't too concerned with the technique in this work, but you can use some either manual or automatic mathematical analysis over these functions and objects to find, in this case, the weakest possible preconditions for each of these program pairs. And these conditions are in terms of the initial stack, the list of values S, as well as the potential input arguments to push U and V. So question is, how do we then construct our concrete condition? Well, that sound commutativity theorem gives us a sort of procedure for doing so. What we do is we say that our concrete condition will hold for a heap if that heap contains a well-formed stack and contains the input or output cells for the 2 programs, and those values corresponding, the list of values for the stack and the values in those cells, those satisfy whichever particular abstract condition we're using for each pair. So then what we get is we can immediately construct derived concrete commutativity conditions for each pair. So note, for example, that for peak and peak, we get that they always commute in the abstract space. But what that translates to in the concrete space is that we at a minimum need that the initial heap has some valid stack and some valid input-output cells. And then the rest doesn't matter because the abstract condition was true. As one final topic, I mentioned earlier that this is amenable to composition of disjoint heap structures. So let's suppose that we have 2 abstract domains, A and B, which each have their own projection function and set of abstract values. We can build a domain A star B, which is analogous to the concrete separating conjunction. So if these are our 2 abstract domains, what happens when we compose them is we don't take an actual product over the entire domains. Instead, the main structure stays the same, but our specific abstract values become all possible pairs of the A values and the B values. And then, when we are mapping a heap into this compound domain, it's in the purview, so to speak, if we can partition that heap into 2 halves, which one half maps into A and the other half maps into B, in which case the value that we map to is the pairing of that A value and that B value. And of course, naturally, those 2 halves have to be disjoint. So one way, there are various nice properties that we get from this composition. Here's just one example that we elaborate on in our paper. Here again, we have the results from our analysis of a stack data structure. Let's say that we have another data structure, a non-negative counter that has increment, decrement, and read operations. And again, we've synthesized or verified using these mathematical analysis techniques commutativity conditions for each of these pairs based on the initial value of the counter. Now let's say that we want to design a concrete data structure that has both a stack and a counter so that we can keep track of the size of the stack. So the programs for that, at least in the abstract space, might look like this, where we say, oh, pushing now both pushes a value and increments the counter. Similarly, pop, there's a typo there, but pop pops a value and decrements the counter. And then peek does the same thing as before, and getting the size of the stack is just reading the counter's value. What's nice is that we can get for free the commutativity conditions for these compound programs, all possible pairs, just by combining the results from our two individual analyses. Now, naturally, we would then want to derive the concrete commutativity conditions for this compound data structure. Caveat, it's a little bit less free because we need a little bit of an additional guarantee about what happens when we compose our programs together. So in particular, for example, we would have to show that our sort of compound operation of push and increment on the independent structures is sound with respect to the concrete operation of, for instance, push sequenced with increment. And this tends to not be very difficult to do, but it is just one extra detail. OK, so to summarize, we've designed a fairly simple abstract domain that lets you lift concrete heap structures and programs and lets you reduce concrete commutativity analysis, which can be rather troublesome, to much simpler, more automatable reasoning about pure mathematical functions and objects, for which a variety of tools and techniques exist for doing this efficiently. And along the way, we're able to collapse together observationally equivalent cases and similarly handle non-determinism of address allocation and also capture the well-formedness of the heap. And as we just saw, it is amenable to compositional results about disjoint heap structures. We have a bunch of things that we'd like to try moving forward with this work. The first is naturally to implement an abstract interpreter. So we've proven all of these results in Coq, but not in a way that's super friendly to automation. So we'd like to implement that and relatedly integrate our analysis with existing techniques for synthesizing or verifying abstract commutativity conditions, which, as I've said, there are various, there's a bunch of research into doing just that. And finally, and this sort of gets back into what Alexandra was asking before, we'd like to try enriching our abstract domain to have a lattice of sets of abstract values. This would allow our abstract programs to also be non-deterministic, and it would allow our concrete programs, if they're non-deterministic in a way that yields non-observationally equivalent outcomes, we don't completely lose our precision. We know, oh, here are the sets of values that are corresponding in the abstract space. And this would allow for us to analyze commutativity, for example, by seeing if the possibilistic outcomes of the two sequencings all match up or if there's a disparity. And we are interested in seeing if such an enriched lattice would then become even more broadly applicable to other heap analyses than commutativity. So that's what I have for you today. Thank you very much. And I'll happily take any questions.
Okay, questions? Yes.
It was a great talk.
Thank you.
I was wondering, so you picked a particular abstract domain to do all your analysis in, right, if I understood right?
Mm-hmm.
So I was wondering if you could sort of lift this to an even more broader theorem that said, you know, any abstract domain that follows certain conditions would suffice for this kind of analysis.
I'm sure that you could. The way that I talked about the development of each piece of that domain is basically how it went in our actual research about it, to be like, well, now you're going to need that frowny face, and you know. But I'm sure that there are ways that you could broaden it and say, well, as long as your domain has properties X, Y, and Z, then it would be amenable to this kind of analysis. Sure. Mm-hmm. Yep. Absolutely.
Okay. Other questions? I have a quick question. Mm-hmm. Are questions of decidability important on how you build your domain? I mean, as you were talking through your stack example, mm-hmm. I was thinking that in one of your definitions, it felt like you would have to prove that two of those sequences were equivalent or not, so sequences of pushes and pops. And if you're not careful, when you add these commutativity conditions, you might end up with, you know, an undecidable problem, whether these two sequences are the same. And maybe this is not an issue in the way you set up your abstract domain, right. But I was actually wondering if there's any question of decidability of the two sort of programs. Or I know you alluded at the techniques, you get the abstractions coming from analysis, but I was not sure what were the concrete things in there.
I'm not sure. what I will say is you might have been able to tell from the examples I used, we haven't concerned ourselves much yet with loops. And I think the moment that you introduce like a question of actually not being sure whether something terminates and dealing with fixed points and these things, which admittedly I'm not super familiar with, I would imagine you start to run into certain problems of even showing the equivalence in the first place is like not super obvious, which maybe in that setting, something like sort of this approximation to say how close, like we can't be sure that they're exactly the same, but how close can we be sure that they get? And then, for example, so the way that this ends up getting used in the real world, so with my former advisor, Eric, we've been working on a project that's ongoing now of a programming language called Veracity, which is a C-style language where you can actually have these blocks of code that you want to commute, and it will find for you a commutativity condition and try to get it to be as weak as possible. And the idea is that it's not most things aren't always going to commute, but actually if they do, it turns out that with certain extra guarantees about serializability, you can get them to run it concurrently. And that's like the main approach of that language. And so what you could have, for example, is let's say that you can get to like 99% sure that the two outcomes are the same, and a checker to make sure, so you say, okay, run them at the same time, because we're 99% sure that this should be fine. And then check if there's an error after you've run them and say, okay, this didn't work, do it in sequence instead. But 99% of the time, you get that benefit of the concurrency. I don't know, but that's something interesting to explore.
Yeah, thanks. Okay, if there are no more questions, let's thank the speaker again. And